Today will be the last lecture for chapter 2, starting, yes, we have covered all the possible, right, actually chapter 2 and part of chapter 3, a little bit of chapter 3. Chapter 3 is actually, in comparison to chapter 2, chapter 3 is easy, if you know, but chapter 3 is a foundation, chapter 2 is a foundation for chapter 3. That is the reason you need to know. So we have looked at, let me refresh you guys. We started with partial fraction expansion, right? Sorry, we started with Laplace transform. We looked at partial fraction expansion. Three cases. We have looked at transfer function. What does transfer function mean? And translational system transfer function. So we looked at two methods in this one. Okay. So the rotational system transfer function is part of your first homework. I want you guys to do it on your own. If you have any difficulties, you can always come to my office and seek help. So does this summarize what we have done? Am I missing anything? So you have KCL, KVL, and we did the impedance method. Okay. There are traditional method, which is just do KCL and KVL. You can also do the impedance method, where we said sum of impedances in mesh 1, all that, right? You should know how to apply KCL and KVL. I don't expect you, even for this one, here we applied the traditional approach and we looked at impedance approach, right? You can apply just impedance approach in, yeah. When you're applying the impedance approach, you're not paying attention to the laws themselves. That is what happens. So you're kind of blindly doing it. You're programmed to do it. Okay. Today what we are going to do is, we are going to look at nodal analysis of complex circuits. Okay. Last class we looked at this, right? You had a resistor, inductor, another resistor, capacitor, and an applied voltage. The question will be something like this. Find transfer function for the above network using nodal analysis or Kirchhoffs current law. Okay. You cannot get away without using Kirchhoffs current law, because, for example, when we go to chapter 3, you will be forced to use Kirchhoffs current law. There you don't have an option. Okay, so it's better that you learn Kirchhoffs current law, and it's not that difficult actually. It's pretty simple. So what you have here is, you're trying to apply Kirchhoffs current law. We define something called admittance. Okay, admittance is what? It's just the reciprocal of impedance. Okay. So you have y of s is equal to 1 over Zs. So here, this is your admittance, this is your impedance. Okay, and this could be I of s over V of s. So what is the admittance? What is the admittance for this, for R1? G1 would be 1 over R1. Okay. G2 would be 1 over R2. Okay. GL, which indicates admittance for the inductor, it would simply be 1 over Ls. And GC, which will indicate admittance for the capacitor, would be Cs. Simple. Okay. What happened? Okay. Okay. This is let's try to apply Kirchhoffs' current law to this circuit. Okay, what you're going to get is so what are the nodes? Can you identify the nodes? The nodes are these. This is node 1 and this is node 2, right? So for node 1, no, because it's just a current does not split here, right? It just flows. So that is, you cannot really, it doesn't really mean anything to have a node there. Here, this one, the current splits here, right? It is one path, but there are two elements. I'll show you how it splits. Voltage source is the source for current. That's where it starts flowing. Okay. Okay. Not okay? All right. So think about, see, we discussed this. So actually this is, it turns out, all right, let's do this, okay? Let's do this from the beginning. What is the current flowing in? There is this current, right? Let's say IR, okay? IL is flowing out, R1 and IR2 is going out, right? So you would write it as IR1 plus, minus IL minus IR2 equal to 0. You agree with this one? This this is for node 1. You can do it either ways. So if you want to do it going out positive, it's the equal to sign will take care of it, right? You can do it either ways. So if you want, you can do it this way as well. Nothing changes because the right hand side is 0. Okay. So what is the current flowing through R1? See, you can say this is VL over S over L of S, right? The second term, the voltage there. This voltage, there will be a drop here, and there will be this voltage. VL is the voltage between these two nodes, right? Voltage between series elements is the same. It does not change. But when it comes to parallel, the other way around. For series it drops, but with parallel, this is the voltage here, VL, okay? Whatever remains, that is applied to this. VS is equal to this plus this, okay? That is what your Kirchhoffs voltage law also says, right? Applied voltage is equal to, it gets divided into the voltage drop. So this, you agree? From this, you can say, what is this now? V S minus VL over R1, right? But this is negative. Got it? If the voltage across these elements is VL, the current flowing through this would be VL over the resistance. You just applied the Ohm's law, right? Now what is the voltage? VL is applied across these two nodes. That voltage is going to get supplied between these two elements. Not nodes, these 2 points, parallel, okay? Not nodes, parallel. Or you can say actually this is also a node. You can treat this as a node and apply voltage. Huh? It depends on what is your question. The question is find transfer function. So transfer function, if it says VC of S over V of S, what is this? Then you don't need this node. Only with these two nodes you can arrive at that transfer function. Got it? If you are applying these two, right, you may not get a value for V of S. Okay? So now what is IR? This voltage gets split into this and this. VLS minus VCS. VL minus VCS over R2 is equal to 0. Got it? So if you write this, you can write it as VL of S minus V of S over R1 plus VL of S, VL over L of S is equal to VC of S minus VL of S over R2. Okay. This is for node 1. Node 2, you already know what the current flowing through R2 is. What is the current flowing through R2? VL minus This is negative. We have to follow whatever convention we follow, we have to follow it consistently. Plus VC this is VC of S over 1 over C of S, right? So the CS jumps to the numerator. For node, this is VC. It moved to the other side. We are saying we are.
Which one did you move to the other side? R2 or
R2.
Okay. So you had to multiply it. Okay, I see. So then on is V is it will be VS minus VLS?
It's VCS.
I'm talking about R1.
R1.
VS minus VLS. Or did they flip?
They flipped, right? So what you want the notation is, the sign convention is current flowing in is negative, current flowing out is positive, right? So this is what we had. Agreed? Current flowing in is negative. Current flowing out, current flowing out. If I just include the negative sign, this is what you're going to get, right? Plus, this is going to remain as it is. We move that on the other side. And you have this for node 2. Node 2, is it clear? Dion, do you see it now? You're right. See, it's the same thing. Current flowing in is actually equal to the current flowing out. It's the same current. So you can write it as this or that. Yes.
I don't you said to apply the negative to the like you must say around. With the negative sign, the second stanza of the row.
So this is the current flowing in. Okay. Now, what are the known quantities? R1, R2, L are known quantities. C is known quantity. We need an expression for Vc of S over V of S. The quantity which needs to be eliminated is VL of S, right? Because we don't know VL of S. You understand? When you're trying to find the transfer function, the transfer function has to be in terms of all known quantities. It cannot be an unknown quantity. So we have to eliminate, we have to somehow get rid of VL of S. Can we get rid of VL of S? Okay. How do we get rid of VL of S? So if I write it in terms of so apply, let's write it in terms of simultaneous equations, okay? So you have one over R1 plus 1 over LS into V L of S. You have R2 as well actually. Minus one over R2 VC of S is equal to V of S. Okay. And similarly, here for node 2, what you have is minus 1 over R2 VL of S plus you have 1 over R2 plus 1 over R2 plus C of S CS to be C of S is equal to 0. Okay. Or you have G1 plus G2 plus LS right. Correct. We'll do that as well. So that is, in terms of admittance, you can look at it that way. Absolutely right. So do you recognize this form? So this is your Kramer's rule form, right? If you're interested in, this is AX plus BY is equal to C, dx plus EY is equal to F. So we are interested in VC, right? Your VC over V of S is equal to what? So if it is Y, you replace this with the terms, right? Is that what it is? You guys remember Kramer's rule? We are trying to find VC. A, B. No? B and Y? B and E, you mean? Okay, you have A, D, C, F. On the bottom is A, B, C, D, right? So you have delta. Okay, so you apply this. So VC of S would be G1 plus G2 plus 1 over LS minus G2 V of S 0 over delta. Correct? So now what you have done? You've eliminated VL of S. Do you see? You have eliminated VL of S. Huh? Yeah, I think that is what the textbook is following. But you don't necessarily. You can do it even just writing R. I'm just trying to be consistent with what our textbook is suggesting. So you can say you can use admittance for the resistance alone. Okay. So you have VC, if I were to write this as transfer function, V of S is equal to, simple, very simple, minus G2 or plus G2 over delta, right? I mean, if you just mention in words that this is delta, that's fine. Okay, so this is the traditional approach. The traditional approach. This is how you would apply the actual laws. Now, if you're think about, as Melvin was suggesting, these are essentially, look at these. These are admittances, right? You see, these are admittances. Admittance, admittance, right? And this is also an admittance. You see that? Even for this one, these are admittances. Everything has been converted to admittance. Do you observe that? Right? So what here, these admittances are connected to VL, node 1. And this is common to node 1 and 2. You see that? This is again common to node 1 and 2. And these are connected to node 2 only, G2CS.
So if we have a mesh of 3 follow the same time.
You could follow the same pattern. Okay? You could simply do this. Okay? I will take some time to just give you the textbook approach as well in this regard. So if you're following the textbook, we use something called Nortons rule to convert the voltage sources to current sources. Nortons law, it says, Norton's theorem, a voltage source in series with an impedance can be replaced by a current source. Norton's theorem. A voltage source in series with an impedance can be converted to a current source so you have I of S here equal to P of S over Z of S. Please understand this Z is you understand what Z is, right? Z is a general notation for any impedance. It could be resistance, inductance, capacitance. Okay? So if you apply this, so this is current source in parallel. Okay? So this is how it will work. You have this. This becomes current source, which means V of S into R of S. So again, this would be your node 1 or VL. This would be node 2, which is BC of S. Okay. You cannot treat this as a node. Okay. You have to be careful how you solve, how you approach this. If you look at this, the way it is converted, you cannot treat that as a node. Okay. What you do is you apply you can look at sum of admittances applied to node 1 or connected to node 1, I think. Yeah. Into VL of S minus Did we have this right? VC of S, V of S. I think we did not have this right. We missed out something here, right? Was it 1 over V? It's R1, right? It has to be current sources. It cannot be voltage. Right? You see this? Right. So you have 1 over R1 into V of S. Just verify. I erased this part, but can one of you verify? I think that is what it was. Yeah, it was V over R1. Huh? 54. But I want you to verify in the notes if you have notes. If you don't have, it is 1 over R1 into V of S. Right. So this becomes, what does this become? G1 into V of S. Got it? So it is sum of impedances and the current applied to node 1. You see that? This is the current applied. You understand what current applied and current flowing is, admittance is connected. There is a voltage source here, so there is a current flowing. It will still remain the same. This would be G1, right? So you have G1, G2, and that is what the textbook also has actually. Yeah. So G1, G2, that's it. G1, G2 over delta.
So we can leave it in that form for our test.
If you are short of time in the exam, you can leave it, but for assignment, I wouldn't want you to leave it. In an assignment, what you want to do is express the denominator as a polynomial in that order, right? Because that is, when you express that, you can take that and put it in MATLAB and solve it. But if you just leave it as delta, you may not be able to solve it, right? So this is how you would approach this. So what you have here is pretty much the same thing. G1 plus G2 plus 1 over Ls into VL of S minus R2 or G2 VC of S equal to G1 into V of S. And the second one would be minus G2 VL of S plus you have G2 plus C of S okay, and here you can apply again Kramer's. So this method, I would strongly recommend that you practice this method on the problems you have been given, and see if, check with me. If you cannot verify whether it is correct or not, check with me and see if that is correct. What we can do is, when we check, we can do the traditional approach, right? And then see if this approach is working. Or what we could do is, what is the other option? You cannot do MATLAB for the physics part. Huh? How to verify? Extra session itself will not. You do voltage law. You do voltage law and verify. Voltage law, if you are much more comfortable with voltage law, you can do voltage. Okay? Please get started with your assignment.